So now, without further ado, I want to introduce Patrick from Redpanda, who's going to give us some really cool technical details.
Thanks. Should I do that? Thanks, Joe. How's the audio on Zoom there? Good? There's still an echo. I think the echo is going to happen regardless.
Okay.
Oh, good.
Right.
All right. Hey, I'm Patrick. I'm here to talk about Redpanda. A little bit about myself. I actually started out coding in C++ back in the day. I was actually working literally in a sweatshop. It was in the garment industry in New York, and I was doing C programming with embedded SQL, building these order management systems. It was a little sweatshop of like, bunch of women like, sewing up stuff. Yeah, so that's where I cut my teeth. I later moved on, just like everyone, into kind of the enterprise Java space. A lot of like N-tier applications, with a GUI, like a web-based GUI and backed by database, that kind of thing. I got into like open source and distributed systems, actually even back in the C days, doing MPI and that kind of thing. I thought it was really cool. And so when something like Apache Hadoop, who's heard of Hadoop here? Yeah. When that came along in the Java and open source space, I was like, oh, great, let me get into it. And I got into big data that way. And today I work at Redpanda. And Redpanda is a product written in C++, as you'll see. But I'm not a C++ expert. All this is to say, I don't know C++ expert. I mostly code in PowerPoint right now. So, and this is all to say that I was a student of C, and I'm just a C student. Right. And so what are we going to cover? We're going to go through Kafka a little bit because if you don't know, who's heard of Kafka? A lot of people. That's awesome. Redpanda is a Kafka replacement. And hopefully that becomes clear. And so in order to talk about Redpanda, usually we need to talk a little bit about Kafka. And then I'm going to introduce you to Redpanda and then go a little bit into the internals, including this thread per core architecture and C star. Who's heard of C star? Okay, great, awesome. That means a lot of people are not going to be able to give me a hard time.
That is a great point.
What's going on?
They can't see the slides on Zoom because we're not.
Oh, how do I do
the
that?
slides? Sorry, one moment.
Zoom?
Yes. And
.us?
yes, let me get the.
Oh, actually, I don't have here.
So sorry.
Good call, though.
And pulling up information. Technical difficulties. 7. All right. Meeting ID 892
892
6814
6814
0472.
0472.
And you want
Should I not connect? I should not.
meeting password 8000 2000 8080. And then you should not connect audio. But then you should be able to share your
I will
slides.
not connect to it.
Sorry.
Okay, are we in here? So now I'm going to share my screen. I'm going to share my desktop. All right, can you guys see something?
Yes.
Sweet. And now you should be seeing it full screen. Everyone else sees you though. Let me close this. We don't need that. All right. Good. This is still, how do I minimize this thing? Just put it all the way to the bottom. Nothing useful is ever in the bottom. Okay, yeah, so we're gonna go through a thread per core architecture, like kind of a little bit of the guts of Redpanda. Yes?
Can you still display the chat window because that's the only way to communicate with us?
Oh.
I have it up. Oh, I have it up here. Yes.
Yeah, it's over there, right?
Yep.
Yeah. Okay, and then I'm just gonna do a wrap up and then maybe we'll have time for Q&A and more beer. And so a little bit about Kafka. Really was first introduced in January 2011. It incubated in LinkedIn and then it was open source via the Apache Software Foundation. The initial use case was to ship HTTP logs into Apache Hadoop. And it being a product of its time, this was a time when Hadoop was huge in Apache world, and it was really designed for like commodity hardware. And commodity back in the day was basically a 2U server, maybe with 2 sockets, 16 cores total, and then like 12 JBots, right? 12 spinning disks. And the idea was to harness all that I/O so you could process big data. And then, big emphasis was placed on locality because anytime you go over the network, that it was like gigabit Ethernet, and like, we just wanted to avoid that as much as possible, right? And Kafka was really designed with like a very similar, kind of core commodity box in mind. It was optimized for throughput. Again, given the spirit of the times, it was written in Java and Scala. It runs on a JVM. It was really designed with Hadoop ecosystem in mind. Because it was built on a JVM, I don't know if you guys and gals are C++ people, but JVM, it does garbage collection. So anytime you give it a lot of heat, you wind up with huge GC processes, which is not great for real-time messaging systems like Kafka. And so what they did is, okay, just don't give it a lot of heat, but it basically uses the Linux page cache to do a lot of, to get a lot of the cache speed up, right? And then it used an external system, Zookeeper, to achieve consensus. Yes?
Just was curious, so does that imply that if you were running Apache Kafka on like a Windows machine, that this would kind of fail until like the modern WSL?
I think anything Hadoop based or like Apache, anything like this, following the Hadoop architecture is going to fail on Windows regardless. Yeah, it's not a good idea. No one runs Kafka or Hadoop for that matter on Windows. So I'm just going to breeze through this because it sounds like most people are familiar with the Kafka concepts, right? Kafka has brokers. Brokers serve topics. A cluster is one or more brokers, typically a minimum of 3, so you can achieve fault tolerance and lose one node and still have copies of nodes. They use a thick client concept where you have producers and consumers. Again, this is kind of big data world, right? You want to avoid network hops. So the clients are expected to basically talk to a central controller to do basically service discovery, figure out, I want to write to a topic in a partition, where should I go, right? So it talks to a controller, grabs all that metadata, and then figures out which exact server it needs to be sending the data to, right? So it's a thick client concept. And there's a kind of an API and a protocol that governs how clients communicate with the brokers. And there's a ton of client implementations out there, right? Primarily in Java, and then there's a C++ client called librd Kafka. And then Rust and Python actually wrap librd Kafka in their client implementations, right? There's also a C# wrapper for librd Kafka. So it kind of covers a lot of languages as far as clients are concerned. There's a controller, like I mentioned, which is basically a designated broker that typically gets elected through a distributed algorithm, right? That serves all the cluster metadata. So, you can do service discovery. Typically what you do in Kafka is you have a comma separated string of brokers, right? And you pass that to the client. The client will go round robin, and like basically the first thing that answers to a metadata request is like, okay, it's okay. I guess you're the right host to talk to, and it works that way, right? So that way you could lose any of those brokers in that list, and you could still have a client be able to reach out and eventually find a controller. So producers and consumers write and read into topics. Topics themselves are really just a logical grouping of one or more partitions, right? So partition is really the unit of work and unit of parallelism. And in Kafka, partition has guaranteed ordering, meaning if you send a message into a partition, then consumers are, have a guarantee that they will replay those messages in the same order of receipt, right? And so very important, like for example, in kind of the market data space, typically what people would do is assign like an asset, like a stock symbol, into a partition. That way all the ticks go into that partition, and when you read it, you see the history of the ticks, right? Yeah, so writes go into a partition leader, and then they get replicated to followers. And this is really how Kafka achieves kind of scale and parallelism, so that you have multiple machines you can go to read your data, and if any one of them goes down, you have a copy elsewhere and you can kind of heal. I already talked about the thick client protocol. And so now we get to talk about Redpanda, right? Redpanda is basically a Kafka compatible RAP-based distributed log that's built on C*, which is a high performance async framework for C++, right? The core of Redpanda itself is a RAP log. Who knows RAP here? Who's heard of RAP? Okay, so RAP is a distributed log algorithm. Came out maybe 10 years ago after Kafka. If it came out before Kafka, Kafka would have been built on RAP, but it came after. But it came before Redpanda, so we're lucky, and we're building Redpanda on RAP. So RAP is a well-known algorithm, extensively peer-reviewed in academia. You'll find it inside Kubernetes, in etcd, it's in CockroachDB, it's in Planetscape, it's in all the databases. They use RAP as their write-ahead model, right? So really proven, really robust algorithm. On top of that, we provide Kafka compatibility by grabbing the upstream protocol definitions from the Apache project. We run that through a code generator, and then that gets hooked into our RAP code. And that's how we're able to talk Kafka. And as a point of fact, we actually don't offer our own protocol. We don't have our own clients. The expectation is that you use the existing Kafka clients to talk to Redpanda, right? And so the result is we basically have a drop-in replacement for Kafka. Anything that runs on Kafka, like link SQL, K-streams, KSQL, all of that runs on top of Redpanda as well. And that whole thing is built on C*, which is really where Redpanda gets a lot of its speed and power, right? A little bit about basics about Redpanda. So Redpanda itself is when you talk about Redpanda, there's Redpanda the company, there's Redpanda the product, but then there's Redpanda really just the core binary. And that's written in C++ 20. It uses things like coroutines. So pretty funky, pretty out there. I'm told by our developers that usually gets a lot of eyes, kind of raised eyebrows, like, oh, you guys use coroutines, crazy. We have other things, like we have a CLI written in Go. We have a web interface written in Go as well. We have a Kubernetes operator. We have Helm charts. Our licensing is VSL, so similar in nature to MongoDB, Elastic. I think it's VSL now, right? MySQL is. The source code and issue tracking are all in GitHub, right? So you can go to github.com/redpandadata/redpanda. You'll see all the code and all the issues. It's not like Apache, like open source, but it's source available. You can grab the code, you can send patches, you can download, compile it, you can use it for free. The only restriction with the licensing is you can't offer a cloud product based on Redpanda. That's what we intend to do. So that's what we do. The core itself is a single binary. So this is in comparison with Kafka, which is JVM based. And then, it requires an external system like a zookeeper for coordination. So, the installation of Kafka is actually pretty complex. With Redpanda, we have everything in a single binary. That includes the core broker functionality. It supports the Kafka API on port 9092. We have inter-broker communications. This is where the RAP protocol goes on 33.145. We have an admin API and a metrics. This is a Prometheus format, metrics exporter, metrics endpoint rather. we have a schema registry. This is something from the Kafka world where this is a place where you deposit schemas for your JSON or Avro or protobuf messages. And so that any consumer can go in there and figure out what's the schema for this message and they can parse it out, right? So in Kafka, that runs as a separate process. And then you have to worry about making it highly available. So you have to have multiple of them with a load balancer and everything. In Redpanda, it's served by the same line. Right, and so the installation process, we also have an HTTP proxy, which conforms to the Kafka HTTP protocol.
Just was wondering, you actually plug in this Redpanda into like another web server, so basically your Redpanda kind of happens to only work with the protocols, and then you have your web server doing other like HTTP stuff combined, or is that kind of or is
Yeah, I don't know if that makes so much sense. Like C Star itself comes with an HTTP server, and that's kind of what we built these on top of, and it's very efficient. And kind of get into that a little bit later. Redpanda can run as a systemd service, or it can run in a container. So we provide a Docker image. We also have RPMs and devs. It compiles for x86 and ARM. So developers love it because they can spin it up on a Mac, like what I have here, and have a Kafka environment running in under a second. And again, like I said, it's written in C Star. It's written on top of C Star, uses C++20 and coroutines. So what does C Star do? Kind of core concepts. C Star introduces this asynchronous thread per core model. And it's one of the ideas, a thread is pinned to a core, right? And these are called shards within C Star kind of language. Each of these shards really work independently of each other. It's like it's a complete shared nothing architecture. Without any, you can limit it via command line, right? But if you just run Redpanda on a server, it will figure out how many cores your box has, and basically say, okay, these are all my shards. It'll grab as much memory as you can. I think it'll leave something like 10% for the OS, right? And then divide that evenly across all those shards. And so from that point on, every single one of those shards can just address that memory. It relies on cooperative multitasking. This is where like coroutines come in, right? Like your tasks have to explicitly yield control back to the scheduler so something else can run for it.
Yeah, this might be something that I'm not sure if you know, but if you have like a coprocessor, like an Intel coprocessor, and maybe a ARM unit, will it recognize those coprocessor cores, or will it just only recognize the ARM CPU cores?
That's a good question. I don't think it will recognize coprocessors at this point. It's really designed for multi-core architectures that in a typical x86 or ARM instruction set. But I don't really know. Yeah, so again, shared nothing architecture, there's no sharing across them. And so it uses this a structured message passing because every now and then these cores need to exchange information. And I'll kind of give an example why later, right? But to exchange information, there's no typically, when you have a typical kind of threaded model where, for example, you have a bunch of network threads that listen on a socket, and then one of them will pick it up, and then that thread will take care of doing everything. But then sometimes it has to do things that are shared with other threads, and you'll use locks and semaphores to basically govern the access of that piece of memory. None of that happens in C Star, right? Because every shard basically has dedicated memory. But sometimes you have to exchange data between these cores, and so C Star has this message passing capability whereby each core has an inbox and an outbox to every other core. right? So it's kind of like actors model implemented in C star, right? So that means no one's ever waiting. There's no locking. There's no blocking. There's a lot of benefits to this architecture, right? Like you got no shared memory. There's no locking, and there's no like if you're doing an I/O operation, you can immediately yield so someone else can run in that core. More importantly, there's no context switching, right? So there's a lot of expense associated with context switching, and there's none of that happening with C star. And you also get core local memory access. Like what we do with Redpanda is we map a partition to a shard. So that partition is always being processed on the same shard. That means there's a lot of contextual data, including the cache, within that shard. And it's going to be in like, it's new as well, right? So you get really fast access to your cache and to the data, to all the relevant data that shard is handling. This also gives us linear scalability. We have a customer. Let me see if I can remember this right. We had a customer ingesting about 10 gigabytes per second on 3 brokers with 56 cores each. That's one customer. There's another one that went from 400 nodes down to 3. But the 400 nodes were like 16 core boxes, and then they switched to like hugely scaled, brokers with like 192 cores. Still less cores than the alternative, right? Yeah, it's still cheaper. But the fact is we can run on these big honking boxes with linear scalability. You really cannot do that with Kafka because then the threads start like bumping on each other, and you get like locking, and it gets ugly. The other benefit for us is that it's easier to tune. Like I mentioned, the thing about listener threads in like typical like threaded application, a typical threaded model where you have to be, like I'm running on this machine, so I'm going to allocate, 16 threads for my listeners, and the rest of them are doing like background stuff, right? It becomes a pain in the butt to tune. But with Redpanda, every core does everything, basically. And so you don't need to worry about that. There's nothing to tune effectively. That's not exactly the case. We have like buffer, we have memory where you can allocate, a certain amount to certain types of buffers and that kind of thing. But as we choose smart defaults. But the fact is, like, you don't have to tune things like number of listeners you have or anything like that. The trade-off is that it's a bit more complicated for a developer. You have some constraints. You kind of like have a straitjacket when you're coding for C star. And the other thing is that it's kind of a viral architecture, meaning you can't just use off-the-shelf libraries. An example of this is actually we have an S3 interface for tiered storage. Tiered storage implementation, which I'll talk about later. We have the ability to offload data to S3, and we just could not use any like S3 library out there because they're not designed in the thread report fashion. There is a way to do it. There's a way to use these in C star data, like the Valiant threads, but you lose a lot of the efficiency associated with our architecture, right? So we had to implement our own S3 client to do that. So it does impose a lot more work on the developers to use it right. And so now going back to Redpanda concepts, right? We have all these same concepts similar to Kafka, brokers, topic, partitions, replicas, right? And we work with existing consumers and producers, like I mentioned. The replication happens via RAP. That's a big departure from what Kafka does. And then the thing we do is that each partition is actually modeled as a RAP group, right? Where in RAP you need odd numbers of everything because the way, one key operation is electing a leader in RAP. Like when anything ever goes down, you have to elect a leader, and of course you need an odd number of voters for there to be a majority, right? The idea is the majority wins, right? So typically you would model like 3 replicas, and the idea is that if any 2 of them are up, then your partition is up and is able to be served. It can accept writes and it can serve reads. The controller itself is backed by a special wrap group. We call it wrap 0. It's basically our control plane. So all the all the cluster coordination stuff, all the cluster metadata that needs to get propagated to all the brokers live in that group. And yeah, the leader, just like everything else, the controller leader and every other partition leader are basically determined through a RAC leader election. So RAC has like its own way of electing leaders and all of that, and we basically implemented that. So this is a right path to Redpanda, which gets into some of the funky stuff we do. So with Kafka, right, your client, first thing you do is, okay, I need to do a metadata request. I want to produce to a topic and a given partition. What I do is I issue a metadata request to figure out which broker should I be talking to for this. Right? So it does that, and then the client finds, okay, I need to find that node. So let's say it figures out it needs to be talking to this node over here. So it finds the right node, and then there's an RPC. So this could come in, it could come in on any core, any one of these RPC in the RPC layer, right? Any one of these shards can basically pick up that connection. And then there's some routing that happens where basically it determines, okay, you're on the right broker, but actually this partition is being served by another core. Let's say in this case, it's core 1, right? And so there's that routing that goes on, and it basically says, okay, I actually need to package a whole bunch of data in my and put it in your inbox. Like, see, there's these boxes over there which are actually representing queues by which all these cores talk to each other. And then at that point, in the Kafka layer of Redpanda, there's a partition object, and that does things like it checks the ACLs, it does some basic checks, and then it determines, okay, this is a legit message. We actually want to replicate it, and then that gets kicked into the RAP consensus layer, which then takes care of replicating that to across the RAP group. And then eventually it hits a storage log object, which kind of takes care of writing it locally to this. Right? In that message passing that happens, we actually do a pretty cool thing, which is we don't actually literally pass the message bytes, which can be potentially pretty big. We use a concept of like zero copy fragmented buffers, and basically we have an allocator that we built where you can allocate like pools of 128 or 64 or 32 kilobyte blocks, and you basically keep a linked list that basically treats these blocks as a contiguous chunk of memory. And it's that structure that gets passed around, not the actual data in those blocks, but that structure that gets passed around. And then there's some funky garbage, like reference counting thing that happens, because in the end, once that request is done and once that other core is done with it, the original core still needs to basically free that memory, right? And so there's some reference counting that happens there, and eventually that data gets free, the memory gets free and gets freed. We have within a RAP group, so I mentioned we use RAP to replicate your data. We also use it to replicate, kind of internal state, like who's the new leader for this partition, and all kinds of things like that. And what that means is that your offsets in terms of the data that the user puts in might be a little bit different from the actual wrapped offsets as we record it in the Redpanda logs. And so we have like an offset translation mechanism for this, to account for that. Because, basically because not all the messages that go through RAP are actually user data. Some of it is control stuff. And then in the storage layer, so eventually this stuff goes into this. C-Star itself has a pluggable I/O backend. We use Linux AIO. Someone's working on an I/O Uring version of that. Right now it's actually not running as fast as the AIO implementation, but that's being worked on. A log is actually, in a partition, partition is a log and it's replicated. But that log is actually consisted of multiple files called segments. And so you always write to an active segment, and then when that segment reaches a certain size, you roll it. You know, typically a gigabyte in size, you close it, and then you write to a new one. And so you have a collection of these segments on disk, right? It looks a little bit like that, right? There's you know, each segment also, when they get closed, we will write out like an index file, you know, kind of to enable for fast lookup of byte offsets. You know, if you come in with a timestamp or a logical offset, like I want to access message at offset 100, you consult that index, and you know, that index will say, okay, in this file it's at this byte offset, right? That's what enables us to do seeds and things like that. Yeah, so we have these indices. Those indexes, though, actually could be deleted, and you can rebuild them just by going through the log and replaying the log and rewriting those indexes. Another interesting thing, we use fallocate to pre-reserve the space for open log segments. I forgot the exact reason why, but it's fairly more efficient that way. More on a storage layer. So your producers are producing logs into Redpanda, and you know, you're writing up log segments. Kafka works the same way, by the way. Kafka also has the concept of log segments. Eventually, if you keep doing that, your disks are going to fill up, right? So within the Kafka protocol or the Kafka spec, they define cleanup policies, right? So what happens, like, how do you not want to, you know, how do you want to clean up some of this data as time goes on? A common one is you just delete all older segments. So that means, you know, you typically, by default, people set like a 1-week retention period, and then after a week, it's gone. Most people don't care to keep that much, right? Like a lot of people keep 24 hours, especially if it's high velocity data, and you know, they don't have that much disk space. The other way is you can compact those segments, and this is if you're using like a key, you know, in Kafka, in the Kafka API, there's an option to use keys. I gave the example of kind of that partition where you take a symbol, you know, that symbol could be the key, and by virtue of that key, it'll get assigned to a specific log, right? But then imagine if you're not interested in the historical value of that stock, you just want the latest. The compaction will basically say, okay, I've seen this key historically, but I can remove all the other, like the older messages, and I'm just going to keep the latest one. Right? That's compaction. And additionally, Redpanda might also do non-destructive operations, like combine smaller segments into bigger ones, just to consolidate small files.
Could you also have another option where some of these statements or these older policies are stored into information database or something like that, or is that kind of
that wouldn't make sense. I would probably go the other way and use this as a write-ahead log for a database, and then store the materialized tabular views in something else. We also, so Redpanda, unique to Redpanda is this concept of tiered storage. I mentioned we have an S3, a capability to move segments to S3, right? So instead of deleting them or compacting them, we'll say, okay, I don't want to delete my data, but I want to move it to a cheaper medium, right? And S3 is cheaper. Like if you're comparing S3 to EBS, it's about 24x price difference. But it is slower. You have a higher latency on read. But yeah, but it's cheaper, so that's an option for Redpanda. And we can still serve reads. Like let's say if you wanted to read from offset 0, which is the very first message you put in there, maybe it was 5 years ago, you can do that. Redpanda will first check the cache, and it'll check the local store, and then local disk, and then it will go to S3 to grab it, right? In a write path for tiered storage, the asynchronous task, the task to upload segments to S3 is actually not in the write path, right? It's asynchronous. So there's implicitly like a little bit of delay. We're trying to get that to like within 5 or 10 minutes, you want your logs to be out in S3. And then we also track metadata about which segments live whether it's in S3 in a local store. And then we, on the read, like I mentioned, like object stores have high latency. I think somewhere between 200 or 300 milliseconds. But what we do is we can, because a consumer fetch request in Kafka, when it comes in, it will tell you, I want to read this offset and I want to read X number of messages, right? And based on that information, you know exactly how much to do to prefetch and read ahead. And so we actually kind of prefetch files as the current file is being served back to the consumer. And so you only take that latency hit once on the first, at the beginning of the request. Subsequently, it streams through pretty smoothly. And so this is great because it allows for virtually infinite retention. Any questions, friends?
There was a question about what the overhead may be like in storage translation logic.
Storage translation logic.
There's an additional abstraction layer between raw data and.
Oh, there is. No, so.
All right, I'll do my best to portray the question of Zoom so I understand it. There's a question about what the overhead may be like in storage translation between raw data
And what's
raw
on
data native storage. Oh, we have seconds.
Yeah, so it's actually, so in Kafka, messages actually come through in batches. And that batch has a certain format. And in Redpanda, we actually take that exact batch and put it on disk. So there's no, unless in cases where you're doing compaction, where you actually need to look at the message content, because the key is part of the logic of how you deal with that message. If you're not using keys, or you're not doing compaction, there's no need to open up that batch at all. And so it literally goes on to disk as it came in on the wire. Does that make sense? I don't know if that answers the question. Yeah, sounds good. All right. The really cool thing about this, about our tiered storage system, is because we have all the metadata context in S3, we actually allow you to spin up other clusters that have read-only access to the bucket in S3. So you can read that data, replay it to consumers, right? And very typical situation is you might have an operational cluster that's doing live ingest, but again, let's stick with market data, right? You're ingesting the market, and then like SEC comes along and you're like, I want to see all your trades for the last 7 years. Well, don't want to do it here because that's just going to screw up your SLAs. What some people do is they pre-replicate it to another cluster. They actually set up a cluster-to-cluster replication so that any kind of queries, any kind of large queries would go on that other cluster. What we let you do with our tiered storage is you don't even have to keep that other cluster up and running. You can just spin up a cluster whenever you need it, point it to the object store, have it serve back all that data, and then when you're done, you shut it down, right? So you can scale down to 0, and that's kind of, yet another way we help you save money. What's all, thread core, big deal, like what's the point? We are orders of magnitude faster than Kafka. A little bit on the throughput side, but Kafka can saturate like your NICs. But the big difference is that if you try to do that with Kafka, you're going to see like big latencies. With Redpanda, we did this benchmark comparing Redpanda with Kafka to gigabyte per second workload. So that's a gigabyte in, a gigabyte out. And we measure the end-to-end latency. So producer basically writes a message. In that message is a timestamp. The producer syncs with the consumer. consumer picks up the message, takes the timestamp, subtracts the delta from the current time, and that's your latency number, right? And we take that latency distribution, and like you can see at the P99.9999, Redpanda is at about 200 milliseconds there at the extreme tail. With Kafka, you're at 70x on twice as much hardware. We tried to run this on 3 nodes in Kafka and it just wouldn't work. So we had to like double the nodes, but then when you do that, you get that latency curve. And then we went to 3x hardware on Kafka, that is 9 nodes, and it was, it did a bit better, kept the tail latencies at under a second. That's still 3x more hardware. But the other great thing is the predictability of the latency. Kafka, you get a lot of jitter, and this has probably, I assume this has to do with like CPU coordination, locking, garbage collection. The page cache is also really bad in Kafka. I mentioned the page cache earlier. Page cache is a generic cache. It doesn't know anything about the Kafka workload. All it knows is this process is trying to open a file, right? Oh, you want that file? Okay, let me put it in the cache. Boom, there you go. So if you try to read like 2 years worth of data, it's gonna vacate your entire cache. And then all your consumers that are relying on a cache for fast access, all now have to go hit disk again, right? So that results in like, that's up. Redpanda latency, like flat. It looks like it looks like the x-axis there. Whereas Kafka on 4 nodes or Kafka on 9 nodes is a lot more volatile. So just to sum things up, why would you use Redpanda? It's faster. Talked about like lower latency, lower tail latency. It's a lot simpler. You do a single binary. There's no JVM. It's a lot easier to tune. There's no reliance on these external systems. We have a nice CLI. We have a nice GUI. And the admin experience. The other thing that Redpanda does that's super cool, you imagine you have a distributed cluster, 20 nodes. We have centralized configuration, and we do that via RAC. We propagate global configuration via RAC. So if you want to change a different parameter that affects all the nodes in the cluster, you just have to do it once, and it gets propagated. So very simple to administer. And then it's super reliable. We are durable by default. So we designed this thing to be basically a database, right? A head log. And so the minute you produce the instant you produce something and you get an acknowledgement back from the broker, you know that thing is durable on disk. It's not sitting on a page cache, it's on disk. So if you lose power, it's still on disk. Again, really predictable performance under load. We also got ourselves audited. We run all kinds of chaos testing to make sure that the results are correct, even if you crash nodes or you introduce latency on the disks or anything like that. We even got audited by Jepsen, which they're pretty famous for taking a microscope and kind of like really inspecting your distributed dirty laundry. Yeah, so we got audited by Jepsen, and they identified some issues. We actually addressed them as of the latest release, and so that's what we got. Our code is on GitHub, right here. Check it out. We have a blog with a lot of nice technical content. We also have a Slack channel, which we urge you to join. We're hiring. We're looking for core engineers to work on this stuff. So if you're into async thread or core kind of thing, we work with some really great engineers. And that's it. Yes.
Sorry about that. This is, I noticed you said that you were using C++. I was also wondering if you had the chance to use like C++ 23 generators and help you with those people that actually or is that
I don't know if that's something that if our engineers looked into, but
Just want to repeat the question real quick.
oh yeah, the question was, have we ever looked into C++ 23? I don't know if we have, and I don't know what kind of constraints they have in terms of being able to move to it. But
Because I think the only issue I have with the generators is, or the code is that without generators, you can't have the your usage of code means, or generators kind of allow you to just write your code with the async, or with the standard coding features, without having to worry about all of these underlying mechanisms and temporarily generated.
yeah, if I was not a C student, I'd probably get into that, but I am. Yes, was there an online question?
Yeah, I got a few of them. One question was asking about the thread per core architecture. What interactions did you guys have with that, with say hyper-threading, or do you want?
A hyperthread is still treated as a distinct core, and so all of that really happens at the chip level. We had a customer that turned it off for some reason. I mean, it's not detrimental to it, but it's just not as fast as a regular, like a physical core. Yeah, I do know that our guy Travis has done a bunch of benchmarking on x86 versus ARM, and ARM seems to come out like more cost effective.
Another question, with the data being stored in S3, are there other tools, analysis to things that maybe interact or can integrate with that, such as Spark or things that
Yeah, if the question is reading directly from object store, that's certainly possible. The file format is like an internal Redpanda file format. We haven't published the actual definition of it, right? It's subject to change because it's an internal format. But I don't, I think short of that, nothing really prevents anyone from doing it. I mean, and it's not that it's not like a secret or anything. We just haven't documented it. Yeah.
So before I ask my question, since you say you are hiring, please tell people the best way that job seekers can contact you. And then I'll ask my question.
You can send email. Maybe let's see if you can contact me here, or you can go to our Slack and get to know people there. You can also reach me on Slack.
The job seeker can send email to BA@redpanda.com.
I wouldn't be handling it personally. I would forward it to one of our HR recruiters and that kind of thing.
Now, ask one question. When you said that you use tech allocators, that's simply a request to investigate the extent to which you would be compatible with other free operating systems. So I noticed that tech allocators is supported on Solaris, but not on FreeBSD. So, what free operating systems do you intend to support?
Right now, only Linux. Right now, I don't know if there's, I mean, I think I don't know if there's any actual restriction apart from really extending our testing matrix, just for all these other operating systems. Yeah, I don't know if there's any other restrictions beyond that.
I'm not making any efforts to be compatible with anything other than Linux.
I mean, right now, frankly, a lot of people want to deploy it on Kubernetes, at which point it's, does it really matter?
Kind of
Yeah.
related question.
Mm-hmm.
So you're doing some kind of async IO, fancy
Mm-hmm.
API, right? The operating systems, you're doing multiple requests for IO.
Mm-hmm.
What are you using? What is it?
It's through C star, but C star backend is Linux AIO. It's Linux AIO.
Okay.
So it's asynchronous already.
Right.
Already kind of very similar to IO Uring, except IO Uring I think covers networking as well and a whole bunch of other device types. I will take some more questions about yes. Okay. To maintain the system? Okay, so the question was, what kind of effort does it take to switch out production from Kafka to Redpanda? And then the second part was, do you need C++ expertise to maintain the system? So like manage it, you mean administer and operate it? I see. So in terms of switching it, whenever you switch platforms, there's usually two burdens. One is you have to refactor your code, or at least recompile and relink everything. And then you have to test it against the new system, because even if the system says that they're 100% compatible, whatever, you don't want to be trusting that, especially if it's mission critical enough that you don't want it going down. So with Redpanda, you get out of doing the first part. You don't have to change the code, and it's actually a pretty big burden, even just recompiling, and because the thing is, acceptance testing, especially in enterprise environments, could take months, even years, and in that meantime, like, you don't want to be maintaining separate branches of your code, right? One that works with Redpanda and one that works with something else. So at least you don't have that. But you still need to test your data, your workloads, and everything on Redpanda. And I'm not just saying that because you shouldn't trust Redpanda, but I would not trust any kind of system, right? Like, you just need to test it against your data and your workload. Question from there's another one there, and then I'll take this one first.
I was actually just going to follow on to that.
Yes.
Customer story.
Oh.
It was literally a drop-in replacement for us, and there was no code change involved. We just pointed at a new set of brokers.
How long did you take to do your acceptance testing?
We looked at it and was like, yeah, that's correct. Yeah, so it was an immediate performance improvement. It was like we saw the orders there.
Awesome. How much did you tune it?
Not all.
Awesome.
Default.
Yeah. And then there was another question over there, right?
You already answered it. I was wondering if there's some issue for authors or
Okay. Okay. One thing, yes. Querying on stream. That all runs on top of Kafka via the protocol. It's not actually part of Kafka proper. So yes, they work on Redpanda as well. Yeah, they work on Redpanda as well. Yes.
So you can use schema registry support.
Yes.
Into the app.
Yes.
So you have one registry that's attached to your clusters.
No, it's actually, so the registry is really a wrap log. You put something in a registry, it goes into wrap, and that log can be served by any of those servers. So basically, we just expose an endpoint in all the brokers to expose. So you would probably take a load balancer and say, you take one host name, put that in a load balancer, and then it load balances across all the brokers, and that's your schema registry.
Based on top of that, so if I had like our production data as a registry, I'm going to use that same registry for a local development that the schema is already seen.
Oh.
Is it normal Kafka computation, or is it like mirroring?
No, I think what you would do is you would just point everyone to that, so you would basically have a cluster that's just for the registry. You could do that, right? It's just like your central registry, which is a full-fledged Redpanda cluster. Might be overkill, but you could run it on like a really small VM or whatever. You could run 3 of them.
You said there's also you could have like a read-only cluster separate to that as well.
If your data is archiving to objects, so yeah, you can do that. Yes.
So if you're trying to build Redpanda source, what would you actually need? Would you just need to use like a GCC only compiler, or would it use GCC Clang, or would it?
I think we use Clang.
Okay.
We use Clang. I don't know the full details of it. It's something, something that I started.
Usually like pipeline to kind of, as well as like a CMake or maybe just a same standard.
Yeah, I believe it's been Let's have a look. What we got? Yeah, you got install dependencies, you got build SH. That looks like a good place to start, right?
So that's CMake.
Oh, there is a CMake. Yeah, they call CMake. Where's the CMake? Ah, here we go. Yeah, what kind of stuff in it?
Yeah, that works.
Yeah, it's good. All right. It works. Yes.
Can you share a bit about Redpanda's business strategy, like source of revenue?
Source of revenue is, if you look at Complement's S1, they say it's a 50 billion TAM. Might be bigger. Right? So there's all the places that Complement already sells to. And then we also have a managed service. So for folks that don't want to have to maintain their own infrastructure or anything like that, they can go to us and spin up a cluster in the cloud. One cool thing that we do in the cloud, we actually have two models. One is kind of like your traditional SaaS, where you go to control plane, you spin up a cluster. That actually spins up a cluster in our account, and then we charge you back for it, right? There's another model, which is bring your own cloud, where we run an agent in your own VPC, and then that agent can basically spin up a Redpanda cluster. It is in touch with our control plane, so it can receive like directives from the control plane, and it also sends out metrics and logs, so we're able to support it, even though everything like your data and your compute are all in your VPC. Yes.
Just one more question. I was wondering if you actually took this Redpanda and tried to make that support on a different machine like a Windows or a FreeBSD machine to get pull requests. What would be the process if you wanted to kind of submit those changes to Redpanda to see if it might be something that you also want to have as
You can, it's on GitHub, you can submit a PR.
okay.
Yes, something from Zoom?
Yes, something from Zoom. Actually, you probably like this question, so I was going to say it near the end.
All right.
What do you kind of credit for what do you most credit for the overall performance gains? Is it more like C++ fast or JVM slow, or was it like your truly architectural changes, the thread per course?
There's a whole, so our CEO has a talk that we can send you the link to this group at some point, but he talks about like the 10 different things that optimizations that he's done, right? Thread per core is probably on like one of the top ones, right? Because the problem is CPU coordination, right? Effectively, like how do you keep your threads from bumping into each other? Well, the answer is shared nothing. And so that's one. The IO buff thing is another one that we built on top of that. The storage engine it's got some optimizations in there as well. Yeah, it's really the thread per core thing. I don't think, maybe the instructions, native instructions are faster to interpret than bytecode in JVMs, but I think more than anything, it's like the non-blocking, the incredible thing is Kafka innovated. If you're an application developer using Kafka, it's great because everything is asynchronous. I'm a producer, I just send, it's in a topic, like someone else is gonna pick it up when they're ready. But when you get to the core of it, you get like all kinds of blocking, right? In like internal to the Kafka design as well. And kind of what Redpanda does is brings that asynchronous communication into the core of it itself, into the Redpanda core itself. Yes.
Actually using all those cores, or do they get parked?
Oh, we can.
If you look at the top, you see like, 10% CPU usage or something, or is it like?
No, actually,
OS?
what you're gonna see is that like maybe one of the two of the cores are gonna be pegged at like 100% because it's actually doing polling, stuff like that, it's. But in all actuality, there's a lot of free CPU time. Like more than anything, you're probably gonna hit like an IO bottleneck, like either on the network or on the disk. We can pump 700 megabytes per second per core. And an NVMe drive can take 1.2 gigabytes per second. So 2 cores, 1 disk, 10 gigabits. That's usually kind of your unit of scaling. You can kind of think of it that way. And we recommend at least 2 gigabytes per core, but the more you give it, the better. Yeah, you could kind of like take that and like boom, 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 and just build, bigger vertically scaled machines.
Yes, I was just wondering, if you were writing this for maybe a different, like a high frequency trading, could you actually like put some